Hello everyone, I am Dr. PSV Shanmukhi, Associate Professor, Department of Physics, Aditya University. Now I am going to explain about the classical free electron theory. At the end of this lecture, student will able to understand the assumptions of classical free electron theory of metals, and you can also understand the merits and demerits of classical free electron theory. Coming to the classical free electron theory, to explain the properties of metals. Properties of metals, Lorentz and Drude, they have proposed the classical free electron theory. That's why this is also called as Lorentz-Drude theory. So according to this theory, means there are some assumptions in this theory. As per this theory, every metal contains a large number of valence electrons. Those valence electrons are free to move randomly in different directions. Just observe, say this is a metal, for example sodium. This contains 11 electrons. So out of these 11 electrons, the 10 electrons are loosely bound to the nucleus, whereas the 11th electron is in the the 10 electrons are tightly bound to the nucleus, the 11th electron is in the loosely bound state. For example, every sodium atom, you can write the electronic configuration as 1s2, 2s2, 2p6, 10 electrons, 3s1. These 10 electrons are tightly bound to the nucleus, whereas the 3s1 11th electron is in the loosely bound state. That means, say this is the nucleus, around this one there are 10 electrons, 11th electron. Actually, in case of one isolated atom, so we can consider this 11th electron is in the loosely bound state, whereas in a metal, all these kind of 11th electrons, they are not concerned to the individual atoms, they are concerned to the entire metal. Suppose this is the sodium metal. In this one, there are so many atoms, say every atom is containing the nucleus, 10 electrons, 11th electron. In the same way, another one, nucleus, 10 electrons, 11th electron. So like that, this metal contains large number of atoms. Every atom is containing the nucleus and tightly bound 10 electrons, 11th electron. Suppose if you don't consider these 11th electrons, what is the remaining part? The remaining part is the sodium ion. That means in the metal, all these sodium ions, they form the core of the lattice. All the sodium ions form the core of the lattice. What about the 11th electrons? They are not concerned to the individual atoms. They are concerned to the entire metal. That means, say this is a metal, all these 11th electrons, they can move freely and randomly in different directions. They behave like gas molecules in a container. They obey kinetic theory of gases. That means, when the electron is moving in this direction, collides with one positive ion core, again moves in this direction, one more collision, that means randomly it moves. That means the free electrons, means these electrons are called free electrons, electron gas. So these free electrons are moving randomly, and while moving they collide with other positive ions, and actually the collisions among the individual electrons is neglected. These free electrons obey the kinetic theory of gases, just like free electrons, means suppose this is a metal, all these free electrons, they are moving randomly, they are treated as electron gas. They are just like the gas molecules in a container or a vessel. So in a vessel, kinetic theory of gases, we know these gas molecules move randomly in different directions. They collide with other gas molecules as well as with the walls of the container. So in this case also, electrons are moving randomly, they are colliding with the positive ion cores. But actually here the assumption is the collisions among the individual electrons is neglected. They are obeying the kinetic theory of gases. Kinetic theory of gases they are obeying. So what is the average kinetic energy of the electron? The average kinetic energy half mv square, it is equal to the average thermal energy 3/2 kT of a gas system at the temperature. Suppose at any particular temperature, the kinetic energy of the electrons in a metal is equivalent to the average thermal energy of a gas molecule in a gas system at the temperature. So like that, these electrons are obeying the kinetic theory of gases. So these are the assumptions. What are the assumptions we are taking? According to classical free electron theory, every metal contains large number of valence electrons. Those valence electrons are not concerned to the individual atoms, they are concerned to the entire metal. They move randomly in different directions, they collide with positive ion cores, and they obey kinetic theory of gases, they behave like gas molecules in a container. The average kinetic energy half mv square is equal to 3 by 2 kT. So these are the assumptions made in the classical free electron theory. Okay, what about this theory? So what are the success of this theory? What are the failures of this theory? This theory successfully explained, it verifies the Ohm's law, it could able to explain the electrical and thermal conductivity of metals, and it could able to derive the Widman-French law, and it could able to explain the optical properties of metals, and it also explained say the paramagnetism. So these things are explained by the classical free electron theory. Actually this could able to explain some phenomena of metals or some properties of metals, whereas this theory failed to explain so many other phenomena of the metals, like say it failed to explain the specific heat capacity of metals, even though it could able to explain the paramagnetism, but it failed to explain the ferromagnetism, antiferromagnetism, etc. So, and say this Widman-French law, it is giving the relationship between the electrical conductivity and thermal conductivity. So that is okay, valid at the moderate temperatures, but at very high and low temperatures it failed. So this could not explain that concept. That means it failed to explain so many other phenomena like photoelectric effect, Compton effect, black body radiation, and ultraviolet catastrophe. All these things were not explained by the classical free electron theory. These are the failures of classical free electron theory. So coming to the summary of this one, actually we have discussed the classical free electron theory. What are the assumptions in the classical free electron theory? What are the merits and demerits? Simply summarizing this one, every metal contains large number of valence electrons. Actually they are treated as free electrons or electron gas, and moreover these electrons are behaving like gas molecules in a container. They obey kinetic theory of gases, they move randomly, they collide with other positive ion cores, move randomly. These are the assumptions of classical free electron theory. Coming to the merits and demerits of this one, this theory could able to explain some phenomena or some properties of metals like electrical conductivity, thermal conductivity of metals. It could able to explain paramagnetism. It could able to explain the Ohm's law, it verified the Ohm's law, and it could able to explain the Widman-French law and so many things. But whereas it failed to explain the specific heat capacities of metals or solids, and also it failed to explain say ferromagnetism, antiferromagnetism, and also photoelectric effect, Compton effect, black body radiation, so many other properties of metals. So these are the merits and demerits of the classical free electron theory. Okay, thank you.